structural engineer or designers, you won't be designing only concrete in your life. Yeah, I do know some engineers who spend 25 years or 20 years only designing concrete slabs. It's maybe good for their lifestyle, but I strongly suggest you to dig into different type of structures, and maybe this is how the market is because of the change in economy and what builders want. So always practice everything. And what I'm trying to say, as we go through the deflection, check and design, try to remember what we did last year, which was we didn't do nothing, only 5 minutes or 2 minutes check. It was one formula to use, and see what we're doing today. That will build a good understanding in your minds as well. So we got a couple of sections, but hopefully I do them within 40 minutes or less, just so you can have careful run through a very good example at the end. So there are some introduction here. It's kind of general. I will take you through. And yeah, deflection, we're trying to avoid deflection for serviceability. So we talked about this from last year as well for steel or timber. What we did up to week 5 was a strength check. We need to make sure the beam will not break and come down due to bending. The other check we did, that was last week as well, shear. Shear is the other action that impacts or stresses. The best word is the stresses our concrete beam. So bending, we talked about it before. Last week we talked about shear. We're good at it, and now we have to check for serviceability. And deflection, it will not collapse and fall down. However, too much deflection will again compromise the standard requirements. So engineers are required to always make sure they document what deflections they had or follow standards. So we need to make sure too much sagging may crack the materials, the walls which supports the slab. The finishing materials, like all the tiles, and if your slabs got deflected more than 20 mil, like larger spans, or 25 mil in shopping centers, then all the tiles and the finish will start, popping up and getting cracked, which is a fault by the designer. Also, if you got a wall built on top of the slab, if it's getting cracked, having those ugly diagonal cracks, that's a mistake. So yes, it is to do with serviceability, and ideally the wall on top of the slab, it's actually can be separating two properties from each other, right? So you may have a wall that will separate two apartments, and if you crack it, that means you compromised the whole purpose, the serviceability of this element. That's why it's coming back to serviceability. And besides the fire isolation and fire insulation, all these kind of things. So it is to do with serviceability, and that's why things have to be checked accordingly. So you're going to be calculating this today, and you as a designer, you're going to check it with limitations like what you did for steel and timber. You still can use the same standard, which was 1170.0, which we used last year. And this year we may give you those limited factors straight away in our examples, right? The third point here is talking about another side of serviceability check. So yesterday, 98% of the lecture is talking about deflection. The last slide in the lecture is talking about crack control, which we're going to practice very well over the slabs lectures. So crack control, it's a serviceability thing. Like we need to make sure we don't see cracks more than 2 millimeter wide, or in the standards, I think they allow. In the standards, nobody will sue you up to 5 mil. More than 5 mil crack, it's a problem. Less than 5 mil, if your design was correct and documented, nobody will come to you. But again, you have a builder to maybe the mix, maybe the way they vibrate. So it's a complicated thing, but eventually it's a team. They all work together. So I think people cannot be, there is a Victorian limitation, like in the Victorian building authority. They got documents which give tolerances to acceptable cracks. Our standards always, if you follow them, they will always get you, not get you to 1 mil even crack. But sometimes if people did not distribute the bars correctly on site, then cracks may start to expand. So the last point here simply is to tell you what kind of provisions and what kind of arrangement designers need to do in order to make sure cracks are controlled. For example, that maximum 300 spacing, it's one of them. There is also formulas we use to make sure that we have adequate reinforcement within the top or bottom side of the concrete in order to control cracks. We will not practice this this week, these kind of checks this week. We're going to practice them adequately in the slabs design because they're more relevant. Cracks don't happen in beams. Beams are small sections, and we already checked them, by the way. And you remember when we place bars in the beam, they're going to be typically close to each other. You will rarely get your spacing more than 300 mil in a beam otherwise, unless you had a band beam, which is flat, and still you can apply the same check. So we're going to practice crack controls over the coming weeks, maybe week 8 or 9 more. But yeah, today is mostly about deflection. So a quick, again, I'm still talking about introduction. We'll just take you through the theory and how the cracks are typically generating, which we talked about for bending. We talked about the different types of cracks. We said there are bending cracks, there are shear cracks, and there are in between. So if I quickly recall that diagram we kind of showed you in the previous weeks, we said to you, if this beam is under positive bending like this, where the maximum M is in midspan, typically here we're going to have vertical cracks going upwards. We call them the pure bending cracks. They are happening due to the tension at the bottom. We have tension, axial tension happening at the bottom side of the beam. Then the shear cracks we discussed last week, they are diagonal cracks, and we know how to call them, to control them, to put the Rio, or we know they are resisted by concrete capacity and steel capacity, etc. And there is here in between, they kind of also sloping gently and in between. Now, what we try to talk about here, we just want to let you sense how complicated are cracks in the reinforced concrete material, which make things complicated, right? And then we're going to take you into the formula. So talking about this part here, we said there are typically primary cracks. So those cracks are primarily that they're going to happen, and then the steel bar is going to control them and prevent them. However, you need to understand in between those primary cracks, there are still micro cracks we don't see, but they're going to be also micro cracks starting in between the primary cracks, and then that will actually cause more complication to this section. What I mean with that, like you remember in the SD2 in the steel and timber, we either had an I shape, for example, or for timber, we had rectangular shape and life was easy. When we go and calculate the inertia, we're just going to use first principles BD cubed over 12. Now, because this is an I shape, we can go back to mechanics of solids and find its own I, but we have our one book tables, one steel book, you remember, tables where we go and find our I effective and all fun. It was all straightforward. After you find those values, you go ahead and put them in a deflection formula and goodbye. Now, no, concrete, it's complicated. It's got all cracks. When those cracks in real life happen, they will change your shape from rectangular to something really weird. So this is a neutral axis, right? And this is the compressed side at the top. So it's intact, no cracks. But the problem here, the question is, what area are we going to use? Right? We don't know what area to use. And that's the challenging or lengthy process we're going to go through today. So that's really what these notes are trying to say. There are cracks progressing randomly into the, that's also a real image of showing you an overloaded. Yeah, I know our beams won't go to that stage, but this is the only stage where we can physically see the cracks. primary cracks which will start, and all the concrete slabs you walk in at university, shopping center, they got primary cracks, but they are very small. They're less than 1 mil or half a mil. You don't see them. You don't see them, right? And they are micro cracks because it's well designed. So as an ultimate design, we designed for ultimate case. Cracks will be generated all over the place, progressing to the neutral axis, and that's where the problem going to happen in terms of finding the inertia value. So basically, these slides are summarizing the story I was taking you through and how we have primary cracks and secondary cracks in the business, which will cause that complication. And we're going to see how we can control those. So those randomized, complicated, different progression of cracks will eventually cause what extra curvature into the RCB. So yes, we know from steel and timber, if we got a piece of timber or steel, they will all get what elastically flexed and curved. That's fine, but we have a good tools to calculate this. And if you remember, I've quickly searched for one of those tables like this one here. Are you guys seeing my screen? I'm not seeing that red frame. Is it okay? Yeah, anyone can confirm? Can you see my screen?
I can see the screen beam bending.
Yeah. Okay. No, yeah, thank you. Just yeah, I'm not seeing that red frame on my. That's fine. All good. Thank you, people. Okay, so you remember last year, or for steel or timber, those materials are homogeneous and isotropic, etc. So they don't have that cracking problem. And we used to use one of those relationships here in that column there. And in SD1, you've actually calculated them and you know from where they came. So you had all the skills there. In concrete, yeah, it would have been possible if this guy was behaving, this eye. The problem is with eye, and just always look at this deflection. It's simple but lengthy. That's what you need to know. So we're still using the same concept, same formulas, but eye is the problem, and eye is the property which we need to carefully go through. Now, this is not only the problem. It's not about only the eye crack that we will spend time in calculating. The other problem is, you know, when we have a simply supported beam like this, okay, you know, the bending moment diagram will look like that. So if we're talking about this span, this middle span, some of the areas here got positive bending, here negative bending, here negative bending. So effectively, this beam is suffering from or experiencing different bending. Sometimes you're going to crack it down, sometimes you're going to crack it up. So see how complicated. So this is another complication added to the business, the story. Is that all? No. Also, number 4 is we got creep and shrinkage. Guys are a bit like the RC structures or elements. They are sensitive to creep and shrinkage, which we talked about in week 1, and tomorrow you're going to be tested about. Yeah, creep and shrinkage. So this is also in the game. And however, the friendly standards gave us very simple formulas to get them involved. I just want to let you know from this comment here or this paragraph that the shrinkage and creep will add what will multiply the elastically calculated after we go and spend all the time and find eye crack and go find the deflection from the eye crack effects and that second effect I mentioned to you. That will give us, for example, maybe 7 mil. Now, by the time we consider creep and shrinkage, it will make it 14 or more millimeters. So see how all these actually are causing more and more complications. The good thing, as I said, with the second one here, with the second item talking about creep and shrinkage, the standards gave us very, very friendly formula. I will show it to you in a few slides and you're going to practice it, which helped us to consider the creep and shrinkage and add it to our deflection. This is called the long-term deflection, long-term deflection. Now, with the with the iCrack business I was talking about, that's where you need to employ some mechanics of solid skills to go and calculate it. We will talk about this, and this summarizing point here was saying that's why it's difficult or a bit lengthy to calculate RC, and it's typically, and yeah, we working with material which there is no relationship to tell us where exactly the crack is moving. There is no such formula. Maybe if you're gonna guys research on the new technologies, you will find a better gauge for that. But yeah, so it's always a formula that we follow, experimental formula to follow. So I trust you've seen this curve before. We are just calling it back here to let you sense it again when we're talking about the deflection design. So you all understand there is a phase. We call it uncracked. That's where we're gonna use the I gross, which is the full inertia of the section. But again, this I gross it's not real, because we're gonna pass this phase by the time we let the slab carry its own weight. By the time we strip and take away the tables, the formwork from under the slab, it's gonna carry its own weight, and then we're gonna pass this stage. This other stage, it is again where we're gonna have most of the shortening, the short-term loading, and again the creep and part of the shrinkage will get involved. If you remember, we talked about the timing of the creep and the timing of shrinkage as well. So some of them will be considered here. In the end of the day, we're gonna be designing for the ultimate case where we're gonna consider the full load expected on the piece of concrete, in addition to creep and shrinkage. And we're gonna talk about how we're gonna consider an averaged I crack. So yes, we don't take the gross I crack. We cannot assume the concrete will stay intact as a rectangular shape or a T shape or L shape, whatever it is. This is not correct. We have to, and on the other side, we will not consider 100% it is cracked. Like you're gonna say, we will not consider a case where it's fully cracked. It's still not right, which someone will say, because your I crack will be very small. So a section like this, where there is only steel bars on the tension side and full concrete on the compressed side. Yes, this is, someone will say, isn't this very conservative? But it's wrong. Nobody uses this. There is an I averaged. We have to kind of use something in between. All right, and that's what our standardized formulas are suggesting us to use. So that was kind of an introduction to just sense the complication of the cracking behavior, which causes the complication in determining basically the inertia of a cross section. And there are other things we need to start knowing about when designing. So here we have two sections to talk about. One is the short-term deflection. The short-term deflection basically will consider the life load, dead load on the slab. And it's nothing to do with the creep and shrinkage, which will be later on added on top of the short term. So the short term process, I think most of our slides are talking about the short term, because inside it, we're going to teach you how to find the I crack average, which is the actual inertia property we use to go and apply it in our deflection formulas. All right, and then calculate the delta. Then that's going to be the short term. Then after section 3, we're going to, section 2, we're going to talk about section 3, which will tell us the standards have shown us very friendly relationship. So delta long term, you're going to see it's equal to the short term we've already calculated plus a factor and function of the short term. Let me just call it F. And then we're just going to beef up the short-term deflection by some factors. We're going to see how it's working. Okay, so in this section, we're just going to go through finding the actual I crack value or the inertia value for a reinforced concrete section. Now, first thing we're showing you on this slide is this deflection formula. Right now, here still we're not talking about the ingredients. The I, which going to take us a lot of time, is this guy sitting here. Now, I just want you to switch a link or start seeing the similarity between this formula, okay, and the formulas that you used before in your engineering education, which is this part here. You remember this table shows you, I just Googled this and searched for it. So it is basically one of the deflection formulas for different cases. Now, this one here, it was provided by the textbook, is just kind of more friendly. It's just instead of showing the calculating the deflection in function of the W, the load, they showed it to us in function of L. That's really the difference. It is same, and then they have a different factor here to cope with the general arrangement. All right, so basically this relationship got similar intent of these ones, but these ones are specific. So if you have a simply supported with point load, you can use this, and it will give you the analytical answer, the theoretical analytical answer straight away. If you have uniform, you simply can use this. This one is just another form, the one that we're talking about here. You can take it as, and definitely you're going to use it in your examples and in your maybe exam or test if you have deflection questions. So this is basically a simplified form of deflection formula, which helps us to determine the short-term deflection delta S. Next, I will talk about its details and ingredients. So let me just quickly talk about this part here. This part, as I said, instead of being a function of the W, the loading, they made it simple because we want to see, as I said to you, one of the problems in concrete designs, it's not about what's happening in one point or one section, like here at the maximum. It's also a function of what's happening at the ends. Okay, that's why we use this friend like easier or better formula where it's going to be in function of the bending at the ends and the bending mid-span. Okay, so that was the reason why we have a different presentation of the deflection formula. It is in function of bending because we understand when we check deflection, it's not only about what's happening at the maximum point in the beam, like what we did for reinforcing bars. We go to the maximum bending and design for it. No, here we have to look at the entire beam, what's happening over the span. And we know here we may have a negative, positive, negative. So how are we gonna put them in this mix? This formula will help us to do this. So M left is the M here, M middle M, so MM, which is the middle M, is here, and M right is it is the moment at the right, which from this continuous beam it is negative. So we're all good with this side. Now L, it is the span. L effective, it is actually now there is just some formulas from the standards that will allow us to reduce the span. You remember in shear when we showed you, like if you have a shear, this is simply supported, or sorry, let's go back to the example you did for shear, which also you studied for the exam. So we had maybe a shear like this, right? I know with this one it won't matter, but the standard allow us to go away from the support. So if we have a linear shear like this, if we have a uniform, I think I will make it with a better sense. I will just use a uniform load. So the shear force diagram will look something like this. That's the shear force diagram, and there is the standard said you don't need to take this maximum shear at the support. You can go by a distance denote. So it's kind of a concession we can use. Same thing, the standards here. They said you don't need to take the full span. So lot. Yeah, you can actually take a shorter span, and that's what we call it, the L effective. We will show you how you're gonna calculate this over our examples. Now, 96 is just a factor. This is the Young's modulus for concrete, which you can get from the standards, and we talked about this in week 1. It's just a property for concrete. This guy, it is where I'm going to spend the other 2 minutes or less talking about I effective. If you know how to get this right, you are on top of the topic. Again, it's a lengthy process, and in your exam or assessment 2 or the final exam, I mean test 2 or the final exam, we will give you part of, maybe, most likely, we will give you part of those steps to get you to the end, because we understand it's long for an exam. Okay, so I've already took you through the details of the equations. I've already mentioned to you what is the problem behind this eye crack. Yes, it was problem because it's not as easy as timber or steel, one figure, and you just take it from a table and put it in the formula and happy days. No, here you have to experience the crack. You have to experience the bending, how it's distributed over the span. On top of that, we have later on, for the long-term deflection, we're going to have the shrinkage and creep in the business as well. So for, as we're saying in this statement here, is telling us for very, very small loads, your section will not be cracked. That means I will be representing the inertia for the section. That's correct, but we cannot rely on this because it's too conservative. Once the cracks develop, then the regions of large bending will actually change to a value I smaller than I gross. Here we're talking about, because of these issues and problems and concentrations, we have to go and calculate our I effective average. So what I'm saying about I effective average, here I'm saying you have to calculate the I crack at different spots. So let me take you quickly to, we have another page which talks about this. So after you're going to be calculating the I crack, for example, if you have this continuous beam, and this is where we need to calculate the deflection over this span from L to R, or from left to right, you have to find an I effective at this spot, and this spot, and this point here. You have to find the I crack on these three spots. Then you average them together as per this formula. So 50% of the deflection going to be impacted by what's happening at midspan, and 25% will be impacted by what's the strength we have here. The other 20%, 25%, the last 25% will be impacted by what's happening here. This is, again, from the standards. That's how we need to average them. If we have an end span case, this is just repeated here. The slides repeated it. If we have an end span, we're going to have a different recipe. So we have no influence from the support because the bending is 0. And you remember that deflection formula was a function of bending. So we don't need to worry about the I crack here. Now here is 50%. Yeah, that's the I effective 50%. And here is the other 50%. So if you want to know about, if you want me to summarize this in the procedures, first you need to calculate the I effective, which is here, which I just I bypassed now. So I'm going to go back and show you how we calculate an I effective on one or at one section, whether here or there or there, because it's a function of loading. So it's changing, right? After you do this, you calculate it at the other spot, at the other end as applicable. So for this case, we have only this end to worry about because here the I is 0. And then you have to average them as shown. You have to take 50% of the I value at C, 50% of the I value at mid, and you've got your I effective average. That will complete that deflection delta S formula I talked to you about. If you have continuous, you're going to use this recipe, and these are just standardized given to us by the standards. So that was about the general. We're talking here about the average value for the effective second moment of area. It's more general I effective value. Now we're going to show you next how to find the I effective for a particular section over the span. Before we do this, I just want you to have a look to this curve, just to sense the story that we were talking about. This steeped line here with sharps, with a sharp slope, it is the case where we have the I gross. The I gross, that not cracked section, which is we cannot use because definitely we're going to crack the section with micro cracks that we don't see. So you see how stiff the beam is, but we can't use it. We're saying, yeah, it's possible up to here, but when the load goes up, it will start getting softer. So, and what about this other dash line here at the lower side? Let's wait for them. Yeah, what about this other slope? That's the case where we have fully cracked sections, and someone will say, yeah, I will use this fully cracked section, but it's too conservative, and your design will be your slab will be very thick, or the beam going to be very deep if you want it to work. So the standard allow us to go somewhere in between, and that's where we try to go and hunt for the I effective, and then we average it I effective average. Okay, that's just to see the things on a diagram so you understand what's the difference between I crack and I gross. These are the two limits, and what we're using is somewhere here, I effective average. That's the actual partially cracked section. So let's come back to, so remember, just taking you back to the main, the main equation that will help us to calculate the short-term deflection. This is all okay, just taking from the actions. This is all straight, this one is straightforward. We're going to show you how to find the effective span. These are straightforward here. This guy, we're talking about this guy. So before we can find the I effective average over the span, we have to find I effective, which is here. And that's where we stopped at just now, which is here. Here we go. And the standards try to guide us and said, use this relationship to find your I effective, right? And make sure it's going to be less than I effective maximum. And you will practice this carefully and also go there and question, as you discussed typically over the workshop, try to make these questions, why is this happening? And then you're going to learn more. So there are a couple of properties we need to calculate typically for this guy here. Some of them you need to employ mechanics of solids, I think most of them. So let's start. I think the slides will show you how we find each, right? I think most of them you've studied them over the past three and a half years. You've studied these things before, but again, we know if we don't practice things for several months, we're going to forget it, so that's fine. So you will need to remember it here. I is the I gross. The first one here is the I gross, which is the easiest. If you have a rectangular shape, it will just be, as you all know, BD cubed over 12. That's it, because it's part of the formula. You see the standards here gave us the formula to go and find this average line. So I don't think, if you have a T shape, just in case, we taught you in mechanics of solids semester 1, 3 years before, how to find the I gross for this shape, and you've done even more complicated shapes, so all good. What about the I crack? I crack, it's again something you can do based on your skills taught or learned from something like mechanics of solids. However, the only problem you have here is we have two materials. So I crack, again, let me tell you, what does crack mean? Crack means you got the neutral axis here, right? Anything under compression above the neutral axis is going to stay intact, concrete, right? Anything below, the concrete will go away, but the steel bars will stay intact. They should be in the concentration or under concentration. So we can have different shapes. We can have this rectangular shape. We can have a T shape like this when the moment is positive, because we're going to be pushing at the top and tensioning the bottom. If the moment is negative, things will be like this. So this side going to be tension, so no concrete at the top, and the lower part going to be compressed, so we have concrete. Now we will let you practice this just to develop a comprehensive understanding, but again, some of our examples will be about rectangular shape. So you're still going to ask me then, all right, we know this is the shape, but how to find the I crack? The other problem we have here is we got two different materials. One is a steel and this is concrete. So S steel and concrete. So from mechanics of solids or from basics, and maybe you didn't study this particular part, is It's not difficult. What we do, we're gonna replace one of the materials to the other. So we have to replace the steel. Typically what we do with concrete, we're gonna replace the steel with concrete by using a factor called modular ratio. What we do is like what they showed us here. What we say, we're gonna say we replace these bars. We're gonna need to go and calculate the area of the steel. Say it's 1,000 millimeter square. That's the area of the 3 bars, right? Then we're gonna multiply it by a factor n. What's n? N is the ratio between the Young's modulus of steel over the Young's modulus of concrete. And then we go and find the equivalent area that can represent the steel as concrete. And then we come to this shape. We have now here a new shape, right, which is a rectangular at the top of the neutral axis. And at some distance, we got another rectangular, which can be considered as concrete. Okay, then from here, but it's very thin. It's very, very thin element. We're going to see this in an example, how we deal with it. So basically here, we're going to just find, again, the I value, which is the I crack. You just have this shape, right? You have this shape, and you need to find the I value of this shape, given that the neutral axis is here. The only step like a new step you're doing here in this subject is you have to convert the steel, and instead of having 3 dots or like the bars, you have to multiply this area by steel by a factor called n. Then you're gonna convert it theoretically to concrete. Okay, and we end up, there is the process of doing this. It is mechanics of solids, basics, fundamental engineering steps. And because the way of we apply, if you remember, we used what we call it first moment of area method. It will eventually, you just need to apply some simple statics. Then you end up, this is again not given in the standards. I want you to know that this equation is not given in the standards because the standards don't show you basics and mechanics of solids equation. So here we're just applying the first moment of area method to go and calculate the I crack, which is something you did in mechanics of solids, and you're going to remember it over your examples, right? The only new thing you have here, we just converted the steel area to concrete area by multiplying it by n. That's all you're going to see this semester. So we're done with the I crack. I'm just stay focused with what we're doing here. We're trying to calculate this guy. And as we said, this guy is in function of this I effective. And we're done with these 2 guys. Yeah. Now we just need to know how to find the cracking moment. Cracking moment, it is from the standards, right? So there is a very nice formula sitting in our standard. And I think I talked to you about it before. We talked about this, how to find M crack, which is the I gross over the tension stress. Now, inside this formula, they have added some properties to consider for this design. So you can straight away go and calculate it. They just made it in function of the compressed stress, because we know we're compressing the concrete side, and we have to go and consider it in our calculations. And maybe we're going to go through these details in the example as well. Just always don't just look at just add some imagination as you look into the parameters and see what they physically mean. So I think by now, there was another property, which is the moment, which this comes from statics. We will show you. The M star was the last parameter in the equation for finding I crack. Sorry, the I effective. Sorry, the I effective formula. The I effective formula. There was the last property we have there. M star short term, and it just comes from the analysis. But you have to only take the short term, which is the WS, and we will talk about this. We don't take the ultimate. We don't take 1.2 by 1.5 dead load, live load. Okay, so you just pay attention to these things to make sure you are driving it in the right way. There are some checks. There are some checks to do because when we hear these slides are talking about finding MS, so it depends on how it's compared with the MCRAC. If it's less, then we can use, there is some kind of, what I'm trying to say, this is really important to say to you guys, there are some shortcuts to do, right? There are some shortcuts to do in finding I effective. If your M star was found less than MCRAC, we can go and say your I effective is straight away equal to I gross. That's how we can, we can. I think we're gonna have a couple of examples which show you this. If your I effective, your I effective can be considered as 60% of your I gross if your steal ratio comes less than the 0.5%. So what I want you to pay attention to is as we go through the examples, there are situations where we can do shortcuts for calculating the I effective, which is then going to let you whether it's going to be same as the I gross or a percentage of I gross, depends on the steal ratio. But this is again depends on what you've been given in the question and how you can drive it from there. You've got a case if your M short term was more than the I crack, then we're just going to go and use the same formula we talked about before. All right, so I think these are all taking you through the notes we discussed, and I've already covered these cases. So after you go and find the IEF, you have to go and treat it over the span. And that's what we're going to do in our example, which we need to start soon. But again, in a test or exam, you may be given one spot to worry about, or you may be told that the I effective going to be same over the span and you don't need to repeat. So that's really a quick go through which takes most of the time, the short-term deflection. Now I'm quickly going to run to in 1 or 2 minutes over the next few steps. So this one is not really too much. As I said, deflection is, here we go. That's all what you need to know. So what we talked about so far is this guy. And I showed you that formula, which is in function of I effective in function of I effective average, etc., etc. So up to now, you should be able to calculate this. Then what we're saying, go and calculate sustained. Now, don't think you need to repeat everything again. It's just going to be a direct relationship. It's just a ratio. You need to, and what's going to change from here to there is the loading. Here, we're just going to calculate the sustained load on the beam, like the dead load. And what's going to stay, the dead load is sustained. We're going to consider it, and you don't need to repeat what we've done before. You just need to use ratio. You're gonna see this how we do it, and then you multiply it by a KCS factor. KCS factor is the creep and shrinkage factor, which we're going to show you how to calculate. Is just a standardized formula. We will use it based on your top end bottom reinforcement, compressed and tensioned reinforcement. So that was about calculating your total deflection. So this is your actual deflection after 20 years or so that your concrete beam will experience. It's coming from short-term deflection when your life load is standing there as sitting, and this is the long-term, which is impacted by creep and shrinkage. If you have no life load there, you're going to be less than delta total. All right, if you don't have life load sitting on your slab, your actual deflection going to be less than total. In terms of limitations, as I said to you before, it's up to 1170.0 standard, which you practiced before and you can visit during the examples as well. That was limiting the deflections we calculate. Now, let me quickly also talk about the method that I was showing you, right? It's called the simplified method to calculate deflection. So all those slides we're going through, 33 slides, it is called the simplified deflection method, which most of the engineers use. You remember with the theta V we talked about for shear, there was a simplified. We use 36 degrees, and there is a refined method, which with theta it's got a lot of iterations. So that's why we leave it to the softwares to do it for us. However, with deflection, most of what we do, we use the simplified method, and we're going through it together now. Now, there is deemed to confirm span to depth ratio. There is kind of a simplified Sorry, the simplified method we did, but here this is, they call it, that's how the standards call it. It's a deem to confirm method, where you just need to use this relationship. This relationship can give you straight away the deflection. Now, which one to use in a test or exam depends on the question. Depends on the question. So you have to study both, yes. And you're gonna see when we get to the slab design, with the slab, we have to start with some sort of feeling about the thickness of the slab. So we're gonna start from using this, something like this. I know this one is for beams, but we have similar ones for slabs. So you need to know it, you need to learn it. It's not difficult. It's just about, again, taking things from the standards. And this is a load, this is the E, these are factors from the standards. This is just that's really straightforward. But what I'm saying to you, it is like if you want to provide some tender drawings, you want to make it, they give you 1 week to quickly sketch up some drawings for the builder to price a job. I would use these formulas to quickly really give me sense about the thickness of the depth of the beams and slabs. So it's kind of a preliminary estimation, but it's safe. It's safe because it's deemed to comply by the standard, but it's not economic. You cannot use it for a big developments. It's not really. And we use it just to give us in the slabs to start with some thickness, and you're going to see them. So you're going to practice using them during your example. And yeah, there are just some straightforward steps, not too much engineering. The last section I will just quickly mention to you. This is the last slide. It's a crack control. This is just kind of a different chapter. Don't mix this slide without whatever I talked to you before. Before was all about deflection calculations. And the main thing you need to focus on is just try to remember some mechanics of solid skills, know how to calculate the I effective, then I effective average, because Mr. I effective average going to sit in a formula which will give you delta S. All right. Now I'm saying it because I teach it, but I know you need time to do it, guys. So as my typical advice is, go through examples, then close your examples, try to solve it without seeing the solutions to make sure you, because maybe some of you are not following. So this slide here is simply talking about crack control, which is just telling you guys there is also for serviceability, for complying with the BCA standards, you have to make sure you have your steel is adequate to control cracks. And we're going to experience this carefully during our weeks when we teach you slabs. And we've already given you some requirements like the 300 spacing, etc. But we will touch on this more. And I think that's really what I want to talk with you. Thanks, people.
Thank you. In the past, the students told me that, okay, Vipul, this is very long examples, 10 pages. My handwritings are big, so therefore it get long, and I try to put all the details for you, every steps, every calculation. So it's that get long, but I will summarize those steps, so it will be short. And as I mentioned in the test, you have limited time, so you don't need to perform all the steps that I'm going to show you, but completeness and probably within 1.5 months time period, you will be graduated and taking similar examples in your real engineering career. So in that case, you might need to calculate all of those details that I'm going to show you. There is not something that is given to you and you just use one equations to calculate it. You need to start from the scratch. So let's do this. Calculate the short and long-term deflections for the prop cantilever beams shown in the figure. Prop cantilever beams meaning, so the prop cantilevers, I think they have not put me the prop cantilevers. Let me plug this one here as well. So these details are given as a part of the examples, okay? So it's part of the questions. So they say that you have a prop cantilevers. So there you go. So you have these prop cantilevers here, where your one side is fixed and another side is supported by roller support. So they have prop cantilever. The beam is doubly reinforced T sections with the dimension and reinforcement shown on the positive and negative moment regions shown in the figure. So they have T sections. given here. That is the positive moments. So the positive moments are here at the midspan. This is positive moment, and at support you have negative moments. So at positive moments, this is your cross sections here, and at negative moment, this is your cross sections here. The loading is given. The dead load 60 kilonewton per meter, live load 40 kilonewton per meter, concrete compressive strength is given, yield strength of the Young modulus of the concrete is given, yield modulus of the steel is given. You can find this modular ratio, N is equal to high modulus of elasticity ratio over lower, so that's 6.6. These short-term factors given to us 0.7. Long-term factors given to us 0.4. Shrinkage strain is given to you in that one. So if you want to extract the short-term and long-term factors, we have a standard score 1170. You remember this one in the SD2. You don't need to carry these standards, by the way. This is just for your reference. Table 4.1 short-term and long-term combined factors. 0.7 based on the different classifications is given in 117, but it's given in our examples. So you don't have to worry, but I'm just showing you that is coming from 1170.0. EC, and this one I think is also given in our standards. If you go back to the section 3. If you go back to the section number 3. Here you go. I think we have 42. So in that case, EC is 30100 EC, and for steel, probably somewhere they mention steel as well. Yep, modulus of elasticity for steels, you have 200,000 megapascal. So all the details are given there. But also already given in this one. So we need to use these equations to calculate the deflection. So we need to find the total deflections. What the total deflection means, that you might have it. Let's say this will deflect something like this. So let's say this is delta total that we need to find. What is the deflection due to live load and dead load? Now you might say that, okay, we learned this one. In our SD2, let's say you have load P and this beam will deflect, let's say delta. So in that case, delta, if you remember this one, then this delta will be PL cubed on 48 EI. And if you have and then you have W and then delta, so you will get delta equal to 5 WL to the power 4 on 384 EI. Now all the details are good, but the trouble is here. Trouble here meaning we don't know I. Well, in here, if you have a steel or something BD, you can find easily BD cube on 12. But if it is made by concrete, then the standard don't allow to use this I gross because concrete crack in tensions. So if it is concrete, and if it is goes, then this portion will be gone. So your concrete is like this, and you have steel bar here. So for that case, the standards telling you that you need to use I effective instead of I. Okay, that sounds good. Where can I find I effective? Straight away, standards give you this I effective on clause 8.5 deflection of beam. There are various methods, 8.51 general, 8.5.2 deflection by refined calculation. There is not much given here about refined calculation. They want you to figure it out by yourself. And then beam deflection by simplified calculation. That is the more focus point here. Clause 8.5.3 and clause 8.4.4 is a deemed to comply reinforcement beam. So there are kind of three methods: refined, simplified, and deemed to comply. So among them, we mostly going to focus our lecture on clause 8.5.3, which is the beam deflection. So in that one, again, you have short-term deflection and long-term deflection, and we combine both of them. Now, as I mentioned, in that equations which I showed to you, like the PL cube on 48 EI, we done the deflections. we also calculate the I. But when it comes to the reinforced concrete beam, we need to talk about I effective, and the equation is given here. That I crack, I. So we need four terminology to get the I effective. So first terminology, you need to find the moment of inertia at crack sections, I crack. You need to find the moment of inertia for I cross. Then you need to calculate the cracking moment. You need to calculate the apply moment. So that sounds good. So let's put that equations here. Where is that equations? Here you go. Delta L square. Let me write that equation. Delta L square 96 EC I effective average and moment at left side plus 10 moment in the middle plus moment on the right side. Okay, so let's find it out each terminology one by one. Length is given to us 9,000 millimeters. Just I'm talking about this one. Where is this given? Here, the length of your beam. EC given to us, Young modulus of the concrete, that is given. That is given here. EC 30,100 megapascals. I effective we need to find. Left side moment and middle moment and right side moments. Now I think the left moment is it would be 0 because here you can see this bending moment diagrams. ML is 0, so that is good. ML is 0. This one in the middle. So let's say in the middles we will have a positive moments, and that is WL square on 16, right? So that's just a bending moment. You don't need to worry about this one. In the test it should be given to you. So what is W? We have two W's, which is the short term and long terms. So let's say this is W that we can get is 60 and 40. So let's say W for a short term equal to WG plus short term factors WQ. 40 kilonewton per meter WG 0.7. What is it? 0.7 here and 60/40. Sorry. So that is 60 and times by 40 kilonewtons per meter. What happens here? Look, this live load is reduced by 30%. Because when you load the beam in the first seconds or first minutes, you don't have all the live loads. Let's say if you are sitting in a new buildings, you will not have all the users starting to use the building in the first 1 minute, first 2 minutes, or very short period, or half a day. The users will start coming in the later of the building. So they say standard said if in the short run you can just reduce your live load by some percentage. So if you simplify that, you might get this one 88 kilonewton per meters for short term. For long term, W, you have WG for long term factors, WQ. So 60 kilonewton per meter again, long term factor 0.4 and 40 kilonewton per meters. So you get 76 kilonewton per meters. Right. So now in this case, let's calculate MM. For short term, let's say for short term, you have W 88 kilonewton per meter times by the length is 9 meters square over 16, and in the middle it would be positive moment. So you get 446 kilonewton meters. And for short term, MR right side would be negative because it's right side here negative MR at the support. So that would be minus WL square on 8 would give you minus short term is 88 times 9 square over 8. You get minus 891 kilonewton meters. So we are finding this ML we found MR we found, we found for short term. Long term, same story. Long term, we will have a but for long term we put 76. So WL square on 16. So 76, 9 square over 16, you get 385 kilonewton meters. And for long term on the right side, minus WL square on 8, minus 76, 9 square over 8, we get 770 kilonewton meters, which is negative. So we found everything. In these equations, we are ready to calculate the deflection, but only troublemaker is I effective average. That's the troublemakers that you can see. We have these all the values. We listed all of them, but we need to find this I effective. How can we find I effective? There is a clause that we can use it. I copy this equation. I effective equal to I crack over 1 minus 1 I crack I gross moment crack and applied moment. So let me copy that equations to calculate I effective. Now, the name for this one is called effective second moments. So I effective equal to I crack over 1 minus I crack on I m crack t on ms squared. It should be, sorry, this bracket should be closed like this, should be less than I effective max. That we need to make the check. Now, let's find out each value one by one, because here we need to find 4 values. I crack by I, we need to find m crack t, and we need to find ms. And we need to do this process for both, because let's say I effective 1, or let's say in the middle, and we need to repeat the same procedure I effective on right side, and we can take the average. I effective average equal to I effective in the middle plus I effective on the right side over 2. So we need to, this is a long process, you can see it's a repeating. So once you know, so we need to find the I effective here, and we take the I effective average. Where it does says that, this states here that for simply supported span and value at midspan. So simply supported, no issue. Like if you wrote a simply supported one, if you have a simply supported one, no issue. What is simply supported? Meaning that this clause says that if you have a simply supported beam one, beam roller, and you have UDL load, you can take the I effective in the middle. That's easy. But if you have multi-span, like for continuous beam, for an interior span, half the mid-span value plus 1/4 of each support value. For end span, so this is end span prop cantilever, half at the mid-span value plus half the value of continuous support. So that's good. It's just the average. We fall in this category, end span, half at the mid-span and half at the continuous support. So it says that half at the mid-span plus half at the right side. So it's just the average, as you can see here. So that sounds good. Let's crack it one by one. So let's do this I first, because we need to get these 4 things. Now I'm not going to write it instead of, because it's very simple to, because the cross sections you can see here, that cross sections given to here is 800 by 1000, and there is a tensile Rio given here, compression Rio gear here for positive moments, and there is a tensile Rio here and the compression Rio here. This is compression tensile Rio, this is tensile Rio, this is compression Rio. Depending on where you're looking here, you will provide the tensile Rio at the bottom, and compression, this is tensile Rio and compression Rio at the top. In here you provide tensile and compression opposite, right? So we have 800 by 1000s. So 800 by 1000s. And now the ultimate goals, because we need to find this I, you remember that mechanics of solid, EMS 1 MS, mechanics of solid, we find the I. Like if someone give you the T section with all the dimensions, you can find the centroid, let's say distance y bar, and you can find the I, right? The moment of inertia for these cross sections, that is your I. Simple. You can just divide this composite section into the 1 and 2. Area 1, 1000 times 120, 1000 times 120, get this area. Y1, you need to take the reference. You need to take the reference, meaning that you need to put the reference line. Let's say my reference line is here. This is my reference line. So for that reference line, you can say Y1 is the centroid of this one. So it's about 60 plus this guy here. So that is 740. You can calculate for this 680 plus 60, 740, as you can see. Now area 2, you can take 300 times 660, and the centroid for Y2, you can take 340. And if you use these equations, that will allow you to use, because we already calculate A1, Y1, A2, Y2, plug the value, you get 488 millimeters. What is that 488? Is your centroid, is your center of your sections. What is centroid represent? It will represent the neutral axis that is passing from this centroid. What is neutral axis? Neutral axis is used in the elastic theory. Like when your sections under the elastic region, when you unload it, go back to the original position. So it will divide your section into two regions. If it is under bending, the top part will goes under compression, bottom part goes into tensions. So that is the importance of centroid. Centroid will going to represent the neutral axis, and that neutral axis divide your cross sections into two regions, compression and tension zone. So that sounds good. And you know this moment of inertia story, that if I have two different composites, I1 and I2, you have BD cube on 12 plus A1 D1 square, B 1000 times 120 square, 1000 times 120 square for section 1 over 12. Area 1, we already calculated. Yeah, and we already calculated. This difference, this is a difference between these guys and these guys. Your centroid for section 1 to the centroid of your whole cross section. So that is difference square. You will get this I1. Similarly, I2, meaning these cross sections here, you will find BH cube on 12 AD2 square. If you plus this, you get I equal to 2 times 10 to the power 10 millimeter power, I think millimeter power 4. Right? So this first thing's done. First thing's done is easy. I. This I, which is the moment of inertia, or you can say gross moment of inertia. This is easy to mechanics of solid year 1. Easy to find. There is not much. You can go through it by yourself if you like, but in the most probably in the test, we will not going to ask you to do this one, right? Because it has nothing to do with concrete. It is just the analysis. It is just simple things. There is nothing concrete. It's mechanics of solid, finding the moment of inertia. So but for completeness of these examples, I have demonstrated that one. So we found I now, that I equal to 2 times 10 raised to how much? 10 raised to power 10 millimeter power 4. And I would be same for everywhere. Same for everywhere, meaning I would be here same, I would be here, they don't vary, right? Because it's under elastic zone. In case if you have different cross section size, you might need to have a different I, but we have 800 and 1000, 800 and 1000. Overall dimension is same, so we have same I value for everywhere. Any questions so far? We found the I, because you see this I sitting here, that's we found. Next step we're going to find is the eye crack. Now there is a eye crack. So what we call this eye crack is a cracking moments, the moment at the crack sections, or say that moment of inertia at the crack or after crack. Let's say after crack. After crack. So that is represented by R crack. So I hope you understand. I gross meaning that you have, let's say you have these cross sections, typical cross sections, and if you want to find this I, you just do the BD cubed on 12. Simple, neutral axis and all elastic. That is represented your moment of inertia I. But if I say that the beam is cracked meaning this part will go off because under the tension the concrete is not good, zero. So all this part is gone. So we are talking about this plastic now. So we need to find a plastic neutral axis, PNA. This is elastic neutral axis, let's say ENA. Now we need to find plastic neutral axis. That is quite challenging because you can see that in the elastic neutral axis, just find the centroid, and your elastic neutral axis will just gonna pass from that centroid. In here, we need to take the different approach. That's I'm going to explain you here. Now, this approach that I'm going to show you, that will be useful only when you have only one material. And in reinforced concrete beam, we have concrete and we have steel. So first goal is to change your steel into concrete or concrete into steel. We need to make it one materials somehow. That's the ultimate. That's the first thing. So the rules is, the simple rule is, it is make the concrete has a Young modulus, let's say 30,000 megapascals, and steel has a 200,000. So you can see that. So the rules is that, okay, if you want to have a selection, which one gonna go, you go for the low elastic modulus things. So you say that, okay, you have a steel and concrete. Should I make everything steel or should I make everything concrete? So generally we have a lowest elastic modulus, we make that as everything. So we make everything concrete. So let's draw at the mid span first. So this mid span one, let me draw up this one. That positive moment. So this is mid span. Mid span, and this is the at support. At support. So let's draw up this one. Thus I draw it up here at mid span. Now what happens? It has, look at this. It has those steels. This guy steels. So it has a 2710 millimeter area square, and you have 3720 millimeter square steel. Now when we convert this one, we make sure that this area that you have steel, it has some strength. It has some strength contribution, some bending strength contribution. So we make sure that we put the enough concrete, the area of the concrete that will be equivalent to that steel. Right? We can't have equals. Let's say I can't put equal to 2710 millimeter square concrete. Why not? Because the concrete and steel has a different Young modulus. So we can't replace the equivalent, the same area that is. So we need to replace by equivalent. So that's what I done here. Look at here, this concrete under this one gone, and you have steel bar. So what we done, we multiply this one. Let's say ES on EC is equal to AST so that is your N. That is your modular ratio. So if I want to find the equivalent concrete area, then I said N AST. Right? So that's equivalent is 6.6 is given in our examples, area of the steel 370. So if I want to replace this steel by concrete, I need about 24550 millimeter square amount of concrete to replace 362720 steel. So that will be good. So we have this one. Now in here, when you replace this steel bar, here you will left with holes, right? While here there is no holes because there is no concrete. Here there is no concrete, so we don't need a hole. But here, when you remove this bar, then you will have empty hole. So we need to fill the concrete in the empty hole. Plus, you need to fill those. You need to replace by the equivalent concrete as well. Therefore, you have n-1 ASC. So n-1 and area of the compression rio. So you need about 12,150 millimeters square of concrete that include filling the holes. So we have to fill those holes as well. So I hope it makes sense. So now we have everything in the concrete. Everything in the concrete means in these figures now, if I use this area, I have no steels. They have everything concrete. So in that case, no problem. You just take the area about the neutral axis. We don't know. This is plastic neutral axis, by the way. And we don't know what is the distance of this neutral axis. So that's fine. We say that, okay, area. Let's take this area, 1000 times 300. So this area is 1000, take away 300 times 120 times dn on times dn times 60. So that is a centroid. You can look at this centroid. Then you have 300, this guy, times dn. That's the area. And the centroid would be dn divided by 2. Plus, you have 12,150 times dn minus 60. That's your centroid. From this point to this point is dn minus 60. So that is the top part, like in the compression side. This is tension side. That is area times the centroidal distance. So from this point to this point is 710, take away dn. So if you just open the bracket, simplify, you will get these quadratic equations. You know how to solve the quadratic equations, right? Minus b square minus 4ac. You will get the dn value 2, but you can choose dn equal to 160. Complicated. This exercise we done it before. Now then you just do the normal things. That concrete 1, you have bd cubed on 12. Area difference ad square. Concrete 2. So concrete 1, concrete 2 meaning this is concrete 1. Let's say this is concrete 1, concrete 2. And again bd cube on 12. Area ad square. Tensile still, there is not much tension here. You can see bd cube 12 is not so it's very small. So tension still is here. This is very small. So I put 0 there. And area and centroidal distance is there. For compression still, again is 0 because there's bd cube on 12 is very small. There is tiny bit. So there is not much value there. So therefore, and this area times difference, you get this. And if you sum them all, you get the I crack 8.9 times 10 to the power 9. I hope it makes sense at midspan. So I crack 8.9 times 10 raised to 9 millimeter to power 4. So I hope it makes sense. It's a lengthy process. As I mentioned again, in the test, we will not going to ask you find I crack because it's not. It's just finding a neutral axis and finding the moment of inertia and all. This moment of this subject does not have a learning outcomes of finding the moment of inertia. The moment of inertia story is covered before in your previous semester. So we don't require your knowledge and skills, but you need to understand. As I mentioned, you need to know. I cannot straight away put this value here and say that I crack is 8.9. Where it's coming from? There is a full story behind it. You don't need to grow. Of course, you can keep these numbers and all very handy if you want to practice it. But you But when you go on the practice, no one gonna give you I-crack straight away. You need to work it out how to get this I-crack and neutral axis. Very same procedures, exactly the same procedures for this guy here. Right side support, that's here. But what is the difference? That your tensile reo goes here and the compression reo goes here. This is compression and this is tensile, right? So in that case, your figure become upside down. Upside down meaning this concrete, this side will crack, so it's gone, and you have this compression side and this is tension side. So again, same story. Your plastic neutral axis is here. Then you replace this guy by N AST. N is your ratio, you remember, ES on EC, and then area. So this is the area of the concrete equivalent to the steels that they will contribute into the deflection calculations. Here, if I replace those guys, I left with the 3 holes. Left with 3 holes meaning, let's say I remove this bar. Let's say I remove this bar and I put the concrete bar here, which is NASC. But then you need to fill the holes. You need to put the extra concrete to fill those holes. So therefore, there is a difference that you have N-1 ASC, which is ASC is your 3,18860. So you get 10 for 20 millimeters square. Once you got this, you have how many sections? 1, 2, and 3. 3 different categories. 1, 2, and 3 different categories, or 3 different sections. So let's do this guys first. I think 36960 on the, this is on the tension side and this is on the compression side. This one, area times this centroidal distance from here to here, which is 740, take away dn. Then you take this 300 times by dn, so you get this area. This is your area times by the centroid is dn divided by 2. Centroid is, by the way, this one a1y1 is equal to a2y2 plus a3y3. There are 3 sections. Area of the section from the centroid to the plastic neutral axis. Area of the second section, centroid from their sections to the neutral axis. Area of the third section, so area of this third section over the centroidal distance. So that is area and centroidal distance. If you just simplify, opening brackets and collecting like terms and so on, and if you use these quadratic equations to solve the dn, you might end up taking dn value about 300, and I think these are a little bit down, but let me find 302 millimeters square. So again, these tables, you remember that this kind of tables, you can just say that, okay, you have these sections, there are 3. And if you just substitute the value, you get the I-crack 10.46 times 10 to the power 9. I-crack 10.46 times 10 to the power 9. Don't feel that I'm just bypassing these details. Look, there is nothing I can teach you critically here. That's you don't know. You are final year, almost graduate engineers. But you let me know in the later on, because of the time constraint, I can't go each number by number. But they are for your completeness. I put the detail. If you go it by yourself, I'm sure you will be able to crack it. This one, nothing super complicated here. I think I explain you everything there. Let me turn on the things before we move. Now, where are we now in terms of finding those details? So we got I-crack. Let's get this MS. Let's get this MS for us. Let me find that MS. Now this MS star at the mid height. MS star, let's say at the mid height, because we're gonna work it out. I think this is at the mid and this is at the support, right? So MS in the mid height. So what is MS? Let's find it out from here. MS is maximum bending moment at the section based on the short-term serviceable load and construction load. So based on the serviceability load and construction load. So MS, we already calculated MS, the applied moment. I believe we calculated MS at the mid height, not long term, short terms. They say short term, by the way. Somewhere they said that. Yeah, short term. So we need to go to short terms, MS, and in the middle. So not locked up, very short terms in MM. So short term MM and let me go to find MS, would be 446. Yeah, that's good. So that would be 446 mm, 446 kilonewton meters. Right? I hope you understand MSM. It's just a structure analysis. It's coming from bending moment diagram. By the way, this is coming from your bending moment diagrams. When you do the bending, and please note, you need to consider the service load. There are two kinds of load. Two kinds of load meaning you have a ultimate load. You know, ultimate load. If you want to have ultimate load, WG 1.2 WG plus 1.5 WQ. Another one is service load, meaning that for service load, you have WG plus SIS WQ, short-term service load. I say short-term. So I hope you make sense. So we are need to use this service load. So MSM is done. Easy, which is good. We done this, we done this, we done this, we done this. Now we need to calculate these cracking moments. Equation is given to you here. The cracking moment is Z FCT.F minus sigma S. I think P, we don't need to worry about this P because it's a tension, is a pre-stress. I can show you where it is P. P here, force in tendons. Tendons mean the pre-stress in the concrete. We don't use tendons, so P equal to 0. So we have P equal to 0. Plus P equal to 0. So our equation becomes Z bracket FCT.F minus sigma CY. Let's do that. So our equations become M crack T equal to Z FCT.F dash take away sigma CS. Let's calculate this Z first. So Z equal to, this is the section modulus, by the way. Z is section modulus. Z is section modulus. Z equal to I over Y. You know this bending equation is equal to My on I. So M equal to I on Y, and this I on Y is Z. So you already calculate I, 2 times 10 raised to power 10. I can show it to you gross here. And Y is 488. So you remember that somewhere 488, the centroidal one. Y distance is the extreme one, 488. You can see this distance 488 from here to here, 488. So this distance 488. So that is your Y. So Y is 488. This is millimeter to power 4, and this is millimeters. So let me plug those values in. 2 times 10 to the power 10 divided by 488. You get about 40.98 times 10 raised to 6 millimeter per cube. Right, so that is there done. FCT.F. Yes. FCT.F. I think if you go back to the chart, you will find that FCT.F is equal to 0.6 square root FC dash is in the close 3.1.13. So 0.6 times square root FC dash is equal to 0.6 times square root 32, and 32 is given in our example FC dash. So you've got 3.4 megapascals. For this sigma CS, what is sigma CS? Sigma CS is given here somewhere here. Maximum shrinkage induced tensile stress on uncracked section at an extreme fiber at which crack occurs in the absence of more refined calculation. The value of signal that account for restraint provided by steel reinforcement may be taken as. So we have 2.5 PW minus 0.5 PCW plus 1.50 PWEC sigma CS. Wave reinforcement ratio for tensile reinforcement, and this one is your wave reinforcement ratio for compression reinforcement. So let me copy that equations for you. Sigma CS is equal to 2.5 PW minus 0.5 PW over 1 plus 50 PW times by Young modulus times by shrinkage strain. So let's get the PW. That is a reinforcement ratio. AST plus APT. APT is your area of the tendons. If you want to find it out, APT, because tendons meaning pre-stress. So we don't need to worry about, because we don't have pre-stress. I can show you APT. APT here, cross-section area of tendons. So we don't need to worry about it. So we can put 0. So AST on BWD. AST on BWD. In that case, AST 3720 millimeter square. Where is coming from? I think we are working at the mid one. So the mid one is this. AST is 3720. The mid and here. So this is here. 100% sits. Okay. And BW, I think the width of your plane, thousands. And depth is 710. Again, I can show it to you here. So that is BW, which is your width, 1000. And depth is 710. So if you measure it from this point, effective date, you remember that 710 millimeters. So that's good. And if you simplify that, you might get 3720 divided by 1000 divided by 710. So you get 5.20, 5.2 times 10 raised to minus 3. So that's done. That's done. Oh, 0. This is PCW, sorry. PCW. Now we have a PC. So PCW. Yeah. Now PCW has an equation ASC on BWD. Where it's given here. ASC on BW. So ASC, you got ASC here, which is 2710. So ASC, let me put 100% back. ASC is 2710 over 1000 times 710. So you got 3.8 times 10 raised to minus 3. So we got everything, EC and everything. So sigma CS equal to 2.5 times this 5.2 times 10 raised to minus 3. We just calculated minus 0.8 times this one, 3.8 times 10 raised to minus 3 over 1 plus 50 times 5.2 times 10 raised to minus 3, EC 200,000. And this shrinkage strain is given, EC and shrinkage strain is given to 1. So EC is 200,000. This is given 800 times 10 to the minus 6. Is 800 times 10 raised to minus 6. Now, in that case, you might get the shrinkage strain 1.7 megapascals. Right, so we have everything now. Everything now meaning that we can calculate M crack T at mid equal to Z FCT dot F dash, take away sigma CS. So Z value we calculated here 40.98. 40.98 times 10 raised to 6. Is it correct? Yep. Millimeter cubed. FCT dot F we calculated 3.4 megapascals, which is Newton per meter square, and 1.7 megapascals. So you get about 70. You get about 69672.131.2 Newton millimeters. You get about 70 kilonewton meters. Right, so that's pretty much everything we got. I think we got everything, the recipe that to calculate I effective, I believe. We got M crack, we got everything. Yeah, so let's do the I effective in the middle. I effective in the middle equal to I crack. Let me copy that. I crack over 1 minus 1. 1 minus 1. I crack on I. And M crack T on MS square. So I think we calculated all. Let me show you how we can plug the values. So I will just show it to you here rather than writing it. If I write it, I will not able to finish it. So I think here you go add. We find this. We plug this value. We find I crack. We find I gross. We found this 70. We found 446. You remember that all the values are found here, right? 70. I crack at the mid. MS we found. I gross we found. So that's value I plug it here. In that case, I get almost same as this one, which is good at mid span. Now we follow exactly the same procedures that for finding the I crack at the support. So when you find this I effective, we need to check. You remember this one? We need to check, meaning when you calculate I effective, you always make this check that is always less than I effective max. Now, how do you find I effective, which is the maximum effective second moment of area, and is taken as I for reinforced sections when P is when this reinforcement ratio is greater than 0.005. So our reinforcement ratio is 0.005 because we calculated that before, right? You can see the reinforcement ratio we calculated. Yeah, 5.2, right? So it's basically 0.0052. So we calculated the 0.052, which is greater than 0.05. So we can take I effective as a I gross. Remember I gross we calculated here. Here. So we can take it and then we compare it that 9 times 10 to the power 9 is less than 2 times 10 to the power, therefore it's okay. We make these checks. Every time when you calculate I effective, you need to make these checks. Otherwise, you need to take it I gross. As Heather mentions, we need to make sure this one. Otherwise, if your reinforcement ratio less than 0.05, you can take I effective equal to 0.61, and then you can make a comparisons. Right, so that's done. Now supports, same procedures. It's not much difference. I crack, MS. You can calculate M crack. You can just go through it by yourself. I'm not skipping it, but there is nothing I can teach you anything here. That's the number change. Okay. Everything I explain you where these equations are coming from, right? They are just the big numbers that you can go through, and you can calculate I crack. You can calculate I crack. Again, make the check that you have 0.08 ratio, which is greater than 0.05. So you can have I effective equal to I, and this check is okay. So once you find these two I effective, you need to have a half, just take it average, right? I show you that one before, right? That you need to take the average where it says, and I will show it to you in the standard as well, that you can take the here. It says that when you have a continuous beam and an end support, you take half at the midspan value plus half the continuous support. So that's half story, and you just take an average. Now we have given these equations. You remember that equations, we have all the values. 9,000, we calculate this, we calculate this, we calculate this, we know this, we know this, and I effective average, you plug this value here, which is I effective, right? I show you this, all the values. Remember that we calculated everything. Where is it? Here you go. We have L, we have ES, we don't have I effective, but now we got it. Now we got it, meaning we have this one. So only hard part is to calculate I effective in this. Once you know the once you know I effective, you are the king. You are the king, meaning you can crack it. Moment on the left side, moment in the middle, moment on the right side. We already calculate all the moments here as well. So that's what I done. That I plug all the values. I show you again. This is repetitions. Look, all these guys are just repeating. So I put 0, 10, 891, 96, this one, you get 10.1 short term. For the long terms, I think long term also we can calculate, but for long terms, we need to, this is short term deflection. And for long term, you can calculate this one for sustain, because you remember there is different moments, right? This is same, but these moments are different because loading are different. Loading are different in the sense that you have a short term loading, which is WG plus 0.7 WQ. And for long term, you have 0.4 WQ. So you have different W. So you have different moments only. So for that case, I need to explain you these factors. This is long terms, but you need to multiply these factors, which is living here, which is long-term factors, is called creep and shrinkage factors, KCS. To take away 1.2 ASC on AST. It's very simple. Area of the compression divided by area of steel, and it should be greater than 0.8. That's checks you need to make it. So I can show it to you. I can show it to you somewhere. I made that calculations for KCS. Yeah, here you go. At the midspan, to take away 1.5, the area of the compression over area of the steel, 1.3, so 0.8 is okay. So here you go, 1.3, you plug the value, sustain load 8.7, you can plug, 10.1 we calculated, so total is 21.41. Now you need to compare against your limits. I can show you where the limits are. If you go back to the start of in the section number 3, here you go, a limit for calculating vertical deflection of beam and slab. So all members total deflection should be delta over LEF 150. I think that is effective there, but for your case, you just take it L over 250. That is, if you want to have effective length. We have not touched this effective length, but I think in the slab we will take you through the effective length, and then you plug the effective length value. So, but for your case, just for your simplification, just if you do these checks, L over 250, L is this one, so you have 36. So 21.41 is less than 36. So we are okay. Our beam is not deflecting so much that exceeding the limits, that exceeding the standard limits. So I hope